Okay, and so for homework 12, we have a weird thing called the square root property that we will be applying to things that look like a quadratic. And I'll be honest, until I went to do this homework assignment, I forgot that this even existed because it is something that you will almost never use in problems 4 and 5. It is something you will use a lot in things like problems number 1, 2, and 3. But if you leave this going kind of like, hey, I don't really like this for 4 and 5, I'm probably not going to remember this. Recognize that Schlegel doesn't remember it either. And that it's kind of a cheap trick that will help you with some sticky situations like 4 and 5. But it is something important that will come up quite a bit in problems like 1, 2, and 3. So if problem 4 and 5 feel a little bit strange, that's because they are. And anyway, with that, we'll get to the yellow box. So feel free to read what's in the yellow box on your own. I am not going to do that. Instead, I'm just going to describe and talk through what the yellow box is really saying. And so what the yellow box is really saying is that if we have something like x squared equals 25, we would need to recognize that in order to get the x by itself or have one x, we need to do the inverse of squaring it. And by the inverse, I mean something like if we had x plus 7 equals 13, we would do the inverse of adding 7 to solve it. We would subtract 7, and that would give us x equals 6. The inverse of squaring something is to do what we call taking the square root, which involves the use of this thing called a radical symbol. And so just like the Teenage Mutant Ninja Turtles radical, that's what we're going to be using today. The red things that I just drew right there are what we call in math a radical symbol. And so that shouldn't say 5 actually, that should say 25, so I'm going to fix that real fast. So we want to find out when x squared is 25, what is the value of x? And so to do that, we take the square root of both sides, and the square root of x squared is going to be x, and the square root of 25 is going to be 5. Now, an important thing to understand about square roots is that a square root will be any number that when you multiply it by itself produces the original number. So for instance, 5 times 5 makes 25, but one that people often forget about is that negative 5 also works, because negative 5 times negative 5 makes positive 25, because two negatives multiplied together makes a positive. So what I'm going to box in blue is one way to answer the question that I created. Another way to answer this question, which is a bit of shorthand and basically just being lazy with not wanting to write too much, is to use this notation that I'm going to box in green that says x equals positive or negative 5. So the answer in the blue box and the answer in the green box say and mean the exact same thing. The answer in the green box is just a little bit shorter to write, and that may be the way that Alex wants you to input the answer. I'm not totally sure what options it will give you about that, but again, the blue box and the green box on the right are both answers to the question, what is the square root of 25? And depending on how Alex wants you to enter it, you can do it that way. I, of course, would accept both, but that's just me. So let's go ahead and get started. We have u squared is equal to 121. And so we want to get u by itself. And so to do that, we need to do the inverse of squaring it, which is to take the square root. And the square root of u squared is u. The square root of 121 is 11. Because 11 times 11 makes 121. But we can't forget u could also be negative 11. Because negative 11 times negative 11 also makes positive 121. And so again, you could put what's in the blue box, or you could put what I'm going to have in the yellow box here, green box, I'm sorry. What's in the blue box and what's in the green box both say the exact same thing. So don't forget your negative components of these things as we work through them. So down to number 2, we have x squared equals 45. Now, 45 does not have a perfect square root, and we're not going to be dealing with decimals or any of that. If we can't take a perfect square root from it, we're going to leave it inside the radical symbol. And so we see that if we want x by itself, the first thing we need to do is take the square root, because that's the inverse of squaring. And so we will get x is equal to the square root of 45. And what's the square root of 45? I don't know. If I was to pull out my calculator on my phone here really quick, I would get that the square root of 45 is 6.7082039325. And what would inevitably happen there is somebody would end up rounding to the tenths place or the hundredths place, and it just does not produce a accurate answer. What Alex is going to want instead is for you to think about 45 in terms of its factors. So let's look at 45, and we can have 1 and 45. 41 is a perfect square, but it won't help us because we would still have a 45 in there. 3 and 15 is another one. 5 and 9 is the other pair. And so I look through that list and I say, okay, are there any that are perfect squares in that list of factors? And there is. 9 is a perfect square. It is a factor of 45 when paired with 5. So we can break 45 into those components 9 times 5. And I like to put the perfect square in front, like the 9 in this case, just because it helps me keep on track with what I'm trying to do. Now from here you could straight away go to this, which is going to be x is equal to the positive or negative 3, because the square root of 9 is 3, and we could have positive 3, or we could have negative 3, and then what would remain in there is the square root of 5. That's totally okay with me if you jump from this step right here to this step right here. I instead am going to do something different just because it has helped me over the years of doing this. And I'm going to include a middle step where I say x is equal to the square root of 9 times the square root of 5. It just helps me see what's happening a little bit better. And so I will now say the square root of 9 is positive or negative 3. Remember, positive 3 times positive 3 makes positive 9. Negative 3 times negative 3 also makes positive 9. So those are both an option. And then you could put a multiplication symbol, but we just assume multiplication if we write the square root of 5 right there at the end. So either one of those is okay. And so again, this is one way to write what the solution would be. I'll box that one in blue. Another way to write the exact same thing would be to say x is equal to 3 square root of 5, or x is equal to negative 3 times the square root of 5. Both are acceptable for me. Alex will probably have a preference one way or the other. But again, the blue box and the green box both have equivalent answers in them. On to number 3. So for number 3, we have something very similar, square root of 12. So we've got x squared is equal to 12. Again, the inverse of squaring something is to take the square root. And so we have x is equal to the square root of 12. 12 does not have a square root. It's between 3 and 4 because 3 squared is 9 and 4 squared is 16. So we're going to have to find factors of 12 that are a perfect square. 1 and 12, 2 and 6, none of those work. 3 and 4 does work though. 4 is a perfect square. So we will write this as the square root of 4 times 3. And again, my personal preference is to split that so I can kind of more easily see what's going on. To be the square root of 4 times the square root of 3. Then I can remember, oh, the square root of 4 is positive or negative 2. And then again, it's assumed that it's multiplication if we have the radical symbol right after it. So we have that the solution here is x is both positive 2 times the square root of 3 and negative 2 times the square root of 3. So another way to write it is x is equal to 2 square root of 3, or x is equal to negative 2 square root of 3. Again, both the blue box and the green box will work in ALEKS. Now's where we start to get a little bit funky. I should go back here. Pause if you need to. Number 4 is where we start to get a little bit funky. And I'm going to show you I'm going to relate this to what we did in lesson 11, and then show you why the method we used in lesson 11 won't work with problems like this. And so sometimes the AC method for factoring, or just general factoring, runs into a roadblock, and there's something that just won't allow us to use that method. This problem will demonstrate that, and so I'm going to call this the old method, which is from lesson 11. And what we would have done is said, okay, we need the whole left side simplified so that we can then factor it, and we need it all set equal to 0. So let's go ahead and do that. So if I was to take y plus 6 squared minus 72 equals 0, and simplify that left side, I'm just going to do the multiplication without showing all the work to keep it a little bit quicker here for everyone. If we were to multiply that out, we would get that, and then we would still have our minus 72 on the end. And so we recognize that we can combine the 36 and the negative 72, which would give us minus 36 is equal to 0. And what we got now is we need to look again at the AC and say, okay, 1 times 36 makes 36. What are the factors of 36? And look for pairs that when I add or subtract them would make 12. And so I see that I can use 6 and 6 to get 12, and that's the only option. So we will split that to be y squared plus 6y. I need 2 plus 6y's because I need to get a positive 12. And then we can do our da-da-da and get y, factor out a y on the left and get y plus 6. And then on the right, I want to create y plus 6, but if I factor out a positive y, I'm left with y minus 6. Well, that doesn't work because now these two don't match. So that's a problem. So let's try factoring out a negative y. So if I factor out a negative y, a negative 6. Did I factor out a y a second ago? I can't remember what I just did. Crazy, so I'll demonstrate it one more time. If I factor out a 6, I'm left with y minus 6. I think I might have accidentally factored out a y when I can't over there, so ignore that if I did that. But we still see that this and this do not match. We have a y plus 6 and a y minus 6. We can't factor that out because it's not identical. So we say, okay, well, what happens? We factored out a positive 6. Let's try a negative 6. That makes it a negative y plus 6. So now our 6's match, but our y's don't. And so this method is broken for problems like this because we cannot create something that looks the same inside the parentheses on both sides there. So instead, we need a different method for problems like this. And again, I mentioned at the beginning of this video that what I'm about to show you is kind of a magic trick. What I would end up doing with problems like this typically is just saying, oh, that doesn't work. And then I would go to what we're going to do later, which is called the quadratic formula. But for problems like this, where we have, and this only works for problems like this, And what I mean by problems like this is this only works for problems that have a quantity like that squared in that blue box that I just drew. Which is one of the reasons why I don't like this. I think it's kind of a waste of time to even teach this to you, because you're not going to remember it and you're just going to use the quadratic formula, which we'll use later anyway. So that being said, there is a method or a little bit of a magic trick for problems that look exactly like this. And that is to say that, oh, we have this. And so what I'm going to do now is notice that I could have a perfect square on the left if I wanted to by doing this. This goes against what we learned in the last lesson, which is another reason why I don't like this. My recommendation to you would be that if you're factoring a quadratic, you always set things equal to 0, like it was at the beginning of this problem. This method, I would get okay at it, I would use it on the test if you need to, and then I would forget about it, because it's not something that's going to come up very often, and it's not going to be helpful in the long run. So again, Schlegel, you can tell, is not a fan of this. So we end up with this. And then we have to say, oh, look, this is kind of cool. Since that's being squared on the left, I can take the square root of it. And I can take the square root of the right side as well. And if I take the square root of y plus 6 squared, I'm left with y plus 6. And then that is equal to the square root of 72. And then I can say, oh, now I can subtract 6 from both sides. And you can do the subtraction now, or you can do the subtraction. Let's actually do the subtraction later. Let's deal with the square root of 72. So the square root of 72 is going to be, we're going to come with factors like we have before, 2 times 36, 3 times 14. No, it's not 14. 24. There's a lot. 4 times 18. 6 times 12. 8 times 9. There's a ton of them. And so we actually have in this instance 2 pairs that have a perfect square in them. We have 2 times 36 and we have 8 times 9. You could use either one, but if you ended up using 8 times 9, you would just have to keep going and do square roots of 8 again, because 8 has a factor of 4. And so in this instance, you want to just select the one that is the biggest number, so 36 in this case. And again, I'm going to say this again. If this is something where you're like, hey, I'm just not getting this, it's going to be one problem or something on the test. This is not a big deal going forward. If this is tripping you out a little bit, but you could do the things before here, life is good. So we're going to break that into that square root of 72 into the square root of 36 times 2. I would again do the square root of 36 times the square root of 2, just to help myself see it a little bit better. And then remember that the square root of 36 is both a positive and a negative 6. So I could have positive or negative 6 times the square root of 2. And then our last step is going to be to subtract that 6 from the left and right side, both, to get y by itself on the other side. And so we get y is equal to positive or negative 6 times the square root of 2 minus 6. And that, everyone, is a lot of work. Recognize that the old method from lesson 11 does not work with problems like this. This new method is a method that is sort of pointless to really put a lot of effort into, because it works on a very finite, small number of problems. And it's probably not something, I don't even remember it, so I don't expect you to remember it. With problems like these, we would end up using the quadratic formula again, which is something that we will be doing in future lessons. So we've got one more like that to do. And so recognizing that the method we used from lesson 11 is not going to work, we're just going to jump straight to this method for lesson 12 and say, okay, we have something that is a perfect square. y minus 6. Since it's a perfect square, I can take the square root of it. So right off the bat, we're going to go ahead and subtract 50 from both sides so that we can have our perfect square on the left. And our constant on the right. So as we've done previously, it's time to recognize that y minus 6 squared, to get y minus 6 by itself, we would take the square root. We've got to do that to both sides. We would get y minus 6 is equal to the square root. Oh, that should be add 50, my bad. I was tripping out for a second because I was going to end up with imaginary numbers, and I was like, what the heck? So that's going to be the square root of 50, not negative 50. Schlegel made a typo. And so y minus 6 is going to be the square root of 50. So again, we need to take 50, break it into its factors. And see if there are any perfect squares in there. There is a perfect square in this pair, which is 25. So we will have y minus 6 equals the square root of 25 times 2. Again, for me, I like to break that into its separate pieces. And then I can see that the 25, I'm going to end up with a positive or negative 5 times the square root of 2. And then the last step will be to clean up that left side. We're going to add 6 to both sides so that we have the y by itself. So again, positive or negative 5 times the square root of 2 plus 6. And that's going to be it for lesson 12. Kind of a heavy hitter on these last two problems. As always, I hope this was helpful, and I hope you have an awesome day.